my pleasure to introduce Erin Teich. Yes, who will give the seminar today. I met Erin for the first time at the March meeting at a real conference, something that we're missing very much lately. So it's a pleasure to see her, even if it's just live. I haven't seen her in a conference for quite some time now. So it's good to have an update of what she's doing. So a little bit of an introduction. Erin did her PhD with Sharon Glotzer at the University of Michigan. And she moved recently, last year, a couple of years ago.
2 years ago.
2 years ago, in the group of Danielle Bassett at UPenn. And I guess today she's going to tell us an update of the work she did during this time. So the floor is yours. And let me remind you, if you have very burning questions, maybe write it in the chat. I'll find a way to interrupt her. But otherwise, let's get all the questions for the end. And then we'll organize a way to ask her questions, either through the chat or you can ask yourself. So Erin, the floor is yours.
Thanks, Laura. Okay, yeah, thank you so much for inviting me and for having me. This is really a pleasure to give a pseudo-international. And yeah, so greetings from the very relieved state of Pennsylvania and the United States of America. I'm glad I can talk to you guys this week. And so I'm going to talk today about disordered jammed systems under oscillatory shear. So they're being perturbed under oscillatory shear. And in particular, how a structural metric that we call crystalline shielding, but it's a very simple metric, localizes a specific type of memory in these systems. So this is work that I did at Penn with Danielle Bassett, and we collaborated with Paolo Ratia, who's an experimentalist at Penn, and his super talented grad student, Larry Galloway. So this is a kind of a theoretical and an experimental collaboration. So before I kind of talk about my current project, I thought I would give a very brief overview of some stuff that I've done in the past, just in case anyone is interested in any of this stuff. Feel free to email me later or, ask questions about this. But yeah, like as Laura mentioned, I did my graduate work with Sharon Glotzer at Michigan, and there I was especially interested in mostly simulations of anisotropic, usually polyhedral particles that only interacted via excluded volumes. They were hard particles. And we were especially interested in local structures of these particles. So I did a few projects related to that. One was we kind of mimicked droplet confinement of different shapes of particles to produce dense clusters. And we kind of categorized the symmetries of these particles based on the shape, or the symmetries of the clusters based on the particle shape. And then we were interested in the influence of local structure on these thermodynamic processes in bulk systems. So including kind of the complicated self-assembly of like a clathrate type phase of these specific particles that had these dodecahedral cage motifs. And then we were also interested in glass formation in these systems. And that was due to competition between very local structures like these aligned or twisted motifs. And then also, I just thought I'd mention, I'm kind of weirdly branching out into a little bit of neuroscience because my current advisor works a lot with the neuroscientific community. And so we're interested in treating white matter in the human brain like a material and doing some structural characterization of this material. So if any of that seems interesting, definitely feel free to reach out to me. But today I'm going to talk about, I think maybe a simpler system. This is just going to be a disordered system of disks in 2 dimensions. And I'm sure for a bunch of people on this talk or on this call, disordered systems are, of extreme interest for a lot of engineers and physicists. And in my interpretation of that is because they're really hard to characterize. and they're really unpredictable. So, and they're all around us, right? As we all know. So, you know, sand is a disordered material that immediately comes to mind. But there's a very non-trivial link between the local structure, this heterogeneous structure that's very hard to characterize in these systems, and the way they behave globally when they're put under some stress. So they carry stress in these extended force chain-like configurations that are hard to predict, but super influential, and can lead to like catastrophic yielding in some cases. So this is an image, I think, of a road in Japan after an earthquake. So that's kind of a scary example of this non-trivial link between structure and behavior. But what I'm going to talk about today is I think a less scary link, but equally as interesting, between structure and behavior in these systems. And that is that disordered systems can store memories. And so what that means is that they can store information regarding how they were prepared, that you can read out later, and you can basically gather with no information about the preparation of the system. You can glean some information about how it was actually prepared just by observing the response of a disordered material under a certain perturbation. So this is a really nice review article about this, if anyone's interested, or if anyone hasn't seen this review article. There's a lot of different ways that memory can be stored in disordered systems. But what I'm going to talk about today is a really simple form of memory, which is just that disordered materials can store a memory of the direction in which they were last stressed. So it's just basically one piece of information. What's the direction in which you were last stressed? And this is a really nice example of that phenomenon. It's a really simple experiment where this is a suspension of colloidal beads between two freely rotating cylinders. And you can apply a shear, or like twist the outermost cylinder, and then measure the torque that's exerted on the innermost cylinder, and it's mediated by the disordered suspension between the cylinders. So if you turn the outermost cylinder in one direction, and then you pause for a second, and then you start turning it in the other direction, the torque that you can measure on the innermost cylinder has this transient behavior, because the suspension between the cylinders has to rearrange in order to transmit the force. However, if you twist in one direction, pause, and then keep twisting in that same direction, there is no transient in the torque that you measure on the innermost cylinder. And that's because the particles have already done all of their rearranging. And so they're storing effectively the direction in which they were last twisted, right? And so what I'm going to focus on today is essentially the nature of this very simple form of memory. And so these disordered structures, or these disordered materials, have very heterogeneous structure. And so does this give rise to essentially like a heterogeneous memory that's spatially localized somewhere because of the nature of the structure of the material? So I'm going to talk today about an experiment that's actually many years old now. This was first published in 2015, but it's kind of the gift that keeps giving, because it's a really beautiful experiment with really nice data. This is a two-dimensional bidisperse colloidal mixture, and it's floating on an oil-water interface. And these particles repel each other on this interface. And so the system is effectively jammed at a pretty low area fraction. So it's an area fraction of something like 40%. And you can actually shear this material in a really controlled manner, which is what makes this so nice. So you can shear this material using a magnetized needle that also sits on the interface. And so by applying an electromagnetic field at a very specific frequency that you control, you can basically control the way that this needle shears the material back and forth. And then by measuring the actual displacement of the needle, right, based on the force that you're exerting on it, you can back out these rheological constants of this material. So you can do some nice rheology here. So here I'm showing, the symbols don't really matter, but The diamonds are the storage modulus of the material as a function of strain amplitude, gamma naught. And the squares are the loss modulus of the material. And so you can kind of have an indication of macroscopic yield in this sample because you can kind of determine when the loss modulus that you're measuring starts to climb, right? The strain amplitude at which the loss modulus starts to climb. For our purposes, the really interesting part of this experiment is that the sample is sheared at a very high strain amplitude prior to data collection at each lower strain amplitude gamma naught. So there's this preparatory step, this shear rejuvenation step, where the material is sheared at a very high strain amplitude, and then there's a pause, and then data is collected at this lower gamma naught. And so we want to know if this material can store this direction of last preparation from this shear rejuvenation step. So let's see if this movie works over Zoom. Does that show up for people? Kind of, it's maybe yes. A little glitchy. This is just to give an indication of the beauty of this experiment. There's a lot of particles in the system, maybe 40 or 50,000. Yeah, and you can see in real time that the particles are rearranging, and you can kind of track that in real time, get some really some really high fidelity results. So I want to convince everyone that this material stores a direction in its response to this oscillatory shear. And the way that I'm going to kind of measure that or show that is via just the local deformation of the system. So here I'm just showing the nearest neighbor shell of a histogram of the nearest neighbors collected over all of the particles in the system. So this is kind of representing the nearest neighbor shell. You can fit an ellipse to that shell, and then you can just track the way that ellipse deforms over time, right, as you're shearing back and forth. And so you can measure both the orientation of this ellipse and how much it stretches as a way of kind of accessing in a kind of a simple manner the local deformation of the system. For an experiment above yield, the picture is pretty straightforward, I would say. So the orientation flips, right, from one orientation by 90 degrees to the other over the course of one cycle. And then the way that the ellipse stretches, or its eccentricity, is basically doubly periodic over one cycle, because it stretches in the first half cycle when the orientation is one way, and then it flips and it stretches basically equally in the other orientation during the back half of the cycle. Below yield, however, the picture is, I would say, more interesting and less straightforward. So there's still, the ellipse is still flipping orientations, right? But during the back half of the cycle, it doesn't stretch as much. So the eccentricity doesn't reach nearly as high a value in any cycle during the back half of the cycle. So this is an asymmetry in the deformation with respect to shear direction, and it's only erased at higher strain amplitudes above yield. So this is a memory, right? This is a memory of a direction. This signal is remarkably consistent. I thought I would just show it over a super large number of cycles to give you guys an idea of how kind of stable this signature is. These are at, so I should say the more yellow curves are the experiments at low strain amplitude, and then the more purple curves are the experiments at high strain amplitude. And just to be perhaps even more convincing, you can take advantage of all this data that you've collected and just do a stroboscopic or a cycle average of these signatures and show very kind of definitively that the system is remembering its preparation, because this stretching during the back half of the cycle is basically suppressed at the low strain amplitudes at these more yellow curves. So for the remainder of the talk, I want to discuss that we think this type of memory is localized within small crystal grains in the system. So it is a spatially heterogeneous memory in this system. This is a snapshot of the microstructure of this mixture. and this is the radial distribution function. And I would say, at least to kind of like my untrained eye, this looks pretty amorphous. It looks, you know, it doesn't look like you can tell that there's much going on. But it's actually a pretty interesting heterogeneous structure. And you can access that in a lot of different ways, but the one that we're choosing for this paper was this kind of agnostic environment comparison way of measuring crystallinity in the system. So all we're doing is we're collecting the environments of every particle. So that would just be this, for example, for this green particle, the set of green vectors pointing to all of its nearest neighbors. And we're comparing that environment with the environments of every particle's neighboring particle, right? So that would be this purple particle. So when you superimpose these and do some matching tricks, you can see how best these environments match, like so how best they lie on top of each other. And if they match to within a certain threshold, then you would say that they're part of the same crystal grain. So you can start to delineate, you know, crystalline particles from non-crystalline particles in this system. And it's agnostic with respect to the actual structure of the crystal grain, right? It doesn't care, it's just doing a simple comparison. So when you do that, then you can segment the system basically into crystalline particles versus non-crystalline particles. So here, all of the blue particles are the ones that are part of a grain of size larger than 2. So just any grain. And all the black particles are the disordered particles. And so you can see that this is a heterogeneous structure. And moreover, I'm sure by eye, you could tell pretty immediately that all of these blue crystal grains have a hexagonal structure if you kind of look, but you can confirm that by, for example, calculating this psi6 order parameter, which is if you're not familiar with it, it's a bond orientational order parameter for every particle that measures basically the degree to which the bonds around a particle have hexagonal symmetry. So when it's high, it's a very hexagonal particle. And so for the particles that we said were crystalline in the sample, that's this blue curve. This peaks close to 1, this parameter, and these are the non-crystalline particles. So this signature, how crystalline a material is, actually is also reflective of preparation memory. So here I'm just plotting the fraction of particles that are crystalline over time, over the entire experiment, for all of these experiments at different strain amplitudes. And after some initial transient behavior, you can see that these signatures are also quite stable, and they basically level off. And kind of you can see already that there's some cycle periodicity here, and there's some asymmetry as well. You can take a stroboscopic average again to kind of clean up this data, and you can see that at low strain amplitudes, there is this asymmetry in this signature, which hopefully is clear if I superimpose these lines. So at low strain amplitude, when the needle or when the shear is in one direction in the first half of the cycle, the crystallinity dips, right? But in the other half cycle, when the shear is in the opposite direction, the crystallinity doesn't dip at these low strain amplitudes. So this is a response asymmetry in the material, and it reflects the local deformation asymmetry, right? So when the material isn't deforming as much during the back half of the cycle, the crystallinity isn't dipping as much for these low strain amplitude experiments. And you can confirm that by just doing like a power spectrum density decomposition of these signals and looking at the first harmonic of the signal. So where you're looking at the period of this signal, and then also looking at the second harmonic of the signal. So that would be when you're looking at twice the frequency of the actual oscillation. And so you can see here that these squares, the second harmonic of the signal, are increasing as a function of strain amplitude, indicating that the signal is becoming doubly periodic. This crystal fraction is becoming doubly periodic as strain amplitude increases. So now I want to move a step further and discuss not whether a particle is crystalline or not, but moreover, where in a crystal grain a particle is located and how this influences its response to this oscillatory shear. So this is a really simple metric. All we're doing is calculating the distance of every crystalline particle to the nearest non-crystalline particle. So this is a very simple histogram binning method where when you measure these distances, there are very clear kind of bins because this is such a geometrical jammed packing. Then you can color basically the particles accordingly or sort them into these bins accordingly. So for example, the blue particles are the closest to disordered particles. So these would be like the grain boundaries of the crystal, of the little crystallites. And then moving all the way to the right, the red particles are the most shielded in the crystal grains, just meaning that they're the most interior and they're the furthest from the disordered particles. This kind of GIF is showing that these crystal grains rearrange over time as a function of the oscillatory shear. So the morphology kind of rearranges over time. And you can see that if you just are plotting the fraction of particles that are in each, the fraction of crystalline particles that are in each shielding layer over time for these different strain amplitudes. So again, this is from the lowest strain amplitude in yellow to the highest strain amplitude in purple for these different shielding layers. So these are the grain boundaries, and these are the most interior, most shielded particles. So these signatures are oscillating, and that's indicating that the actual morphology of the grain is changing over time. Okay. So we can be more precise about how crystalline interiority or crystalline shielding influences how particles rearrange by specifically looking at some metrics that measure rearrangement. So I'm going to discuss two metrics in particular. One is kind of a more traditional metric. That's what I'm going to discuss right now. In the community, it's traditional to refer to this D2min quantity as quantifying rearrangement. It's a little tricky to calculate, but it's super informative. It's a beautiful metric. And then I'm going to discuss a less traditional way of quantifying rearrangement that gets at the same information, but it's easier to calculate. So I'm kind of going to show these two things. So first, this D2min metric it was first proposed many years ago now, however many years, over 30 years ago. No, over 20 years ago. And it's a per particle quantity that's indicating the degree to which the local neighborhood around a particle deforms in a way that's non-affine in a particular time interval. So in this notation, between time t0 and time t1. So it's just basically determining the residual of the deformation surrounding, of the neighborhood surrounding particle I, the residual between the actual deformation and then the, oops, sorry. Is it up now? Okay. The residual between the actual deformation and then the best affine fit to the deformation. So when this quantity is higher, then that means that the deformation of the neighborhood is more non-affine, and it's an indicator that the particle in question has probably rearranged. And so here we can just calculate this quantity over the course of a cycle for all of these particles in these different shielding layers. So we take T0 to be the beginning of a cycle, and then we look at T1 at different points during a cycle, and we average D2 min for each of these layers, for all the particles in each of these layers. And we can see that for this experiment, a very beautiful stratification occurs where the more shielded particles are rearranging less, right? Because these average values of D2 min are lower at all points of the cycle. And the less shielded particles are rearranging more, right? We can also do a sanity check where instead of showing these average values over the course of one cycle, we can just take an average over every pair of times over the whole cycle and just have one average value for each shielding layer as a function of strain amplitude. And we can see that this kind of hierarchy occurs at most strain amplitudes where the more shielded particles are rearranging less. So these average values are lower. And as you would absolutely expect, right, as you decrease in strain amplitude, the particles across the board are rearranging less because these values are decreasing, right? And as an aside, but I think this is a really nice connection, this result that there's kind of a hierarchy of rearrangement depending on interiority within crystal grain is in agreement with and an extension of previous work that sees that particles at grain boundaries themselves are the most mobile and the most stressed when you're under shear. So these are some examples of that. This is actually an analysis from the original paper that published the experiment that I'm analyzing. They calculated psi6 for the particles in this system, and they saw that for the particles with lower values of psi6, that would be at grain boundaries, more particles were rearranging at all strain amplitudes. This is a simulation. This panel D here is a simulation of polycrystalline aluminum, I believe. And the particles are colored by this machine learned softness parameter. If you're familiar with that basically gives an indication of the propensity for rearrangement of particles in the system. And so you can see that there are these big grains that aren't soft at all. And then on the grain boundary, there are these soft particles. And then finally, this is an experiment. This is a colloidal monolayer that's polycrystalline. That's also under shear. It's angular shear this time. And they're actually highlighting all the particles that have large local stresses. And you can see that these particles outlined in black here are indeed on grain boundaries. So our results agree with that, but we kind of go a step further and we say, you know, actually there's a hierarchy here where the more interior within the grain you are, actually the less you rearrange regardless. So in the time I have left, I'm going to talk about the easier way, I would say, of quantifying particle rearrangement, and then draw some conclusions about preparation memory using this kind of easier way to talk about rearrangement. So you can also access the way that particles structurally rearrange once you've delineated which particles are crystalline and which aren't, by just looking at a simple correlation in time. So this would just be the probability, it's a conditional probability that at time T0, if a particle is in a certain structure S, and this would be either a crystalline or a non-crystalline state, that it's still in that structure at time T1. And when we calculate those conditional probabilities for all of these different particles in these different shielding layers, the stratification isn't quite as, you know, it's not quite as beautiful, I would say, as in the D2min case for this particular experiment, but it's accessing the same information actually. So when this probability is high, right, that's indicating that's happening at the same time as D2min values are low. So it's a more structurally correlated layer, set particles in a layer at this specific time, and that's indicating that they're kind of rearranging less in this time interval. And the least shielded particles have the lowest correlations, the lowest probabilities, and that's indicating that they're rearranging more, right? You can combine all of this information for all of the different experiments. So here I'm just showing this, really simply just this, the D2min metric against the structural correlation for all of the different experiments. So the different symbols are different strain amplitudes for these different layers. And so these curves really collapse in a pretty nice manner and show kind of this inverse relationship between probability and D2min. So as the structural correlation gets lower, D2min gets higher across all these experiments and for these different layers. And so kind of finally, I want to address maybe, you know, this, I don't know if this is the elephant in the room or not, or if I've been staring at these plots for too long. But there's a very clear asymmetry in this signature itself, right? Particles in all shielding layers are rearranging more in the front half of the cycle than in the back half of the cycle for this experiment. And that's also indicated by this correlation where it's deeper here than it is here. So that's indicating an asymmetry with respect to shear direction, which is the thing that we kind of set out to probe with this experiment. So we can access that information directly by looking at structural correlation in a half cycle interval, right? So it's the probability that you're in the same structure at a certain time t, if you were in that structure half a cycle earlier. And so that's directly probing the correlation with respect to shear direction. So for these different crystalline layers from the least shielded to the most shielded down here for this experiment below yield, you'll notice that for the most shielded particles, this signature is indeed actually quite asymmetric with respect to shear direction, right? So particles in these more shielded layers are more correlated between times of more and less stress. And for an experiment above yield, this correlation kind of goes away, or this asymmetry basically goes away, and these signatures become more symmetric with respect to shear direction, indicating that they're responding equally when the shear is in one direction as when the shear is in another direction. It's erased above yield. And we can quantify that by, again, just taking a power spectrum, looking at the power spectra of these signatures and looking at the second harmonic of these signatures normalized by the first harmonic. So if the second harmonic is high, we know that that's a more doubly periodic signature and a more symmetric signature with respect to shear direction. So when we do that as a function of strain amplitude again, this is this kind of normalized second harmonic signature, we do see that this kind of nice hierarchy is preserved for all these strain amplitudes, where the more shielded particles have lower second harmonic signatures in this correlation, indicating that they're more asymmetric with respect to shear. And indeed that this asymmetric kind of crystallinity signature is localized within these grains. So the more shielded particles are really preserving the asymmetry of the crystallinity in these systems. So with that, I'll conclude. So or hopefully I kind of demonstrated that crystallinity is a quantity that encodes preparation memory in these systems, and correlations in crystallinity can indicate particle rearrangements. And with that metric, we're showing that particles that are more shielded are less likely to rearrange, and they kind of localize the memory that these materials have of the direction in which they were last prepared. Thank you to my collaborators on this project. They've been super wonderful to work with. And this paper is currently under review, but you can check it out on arXiv if anyone's interested, or feel free to get in touch with me if you have any questions. So thank you, and I can take any questions if there's time.